Okay, so we talked about, where am I here? Enthalpy in organic chemistry, delta H, and we talked about entropy, right, which is the change in entropy would be delta S. Now I'm going to put these two terms together to give us some kind of a measure that's very powerful in organic chemistry called free energy, right? So it turns out these are both energetic terms. We can combine them in an equation that looks like this. This is Gibbs free energy. Now, Gibbs free energy is the change in enthalpy of a system, and the difference between that and the change in entropy by a factor of temperature. All right, so the overall energy of a system, the free energy of a system, is the combination of these two terms. Now, if delta G is negative, if it's less than 0, then we say a reaction is spontaneous, and that is, it's likely to happen, okay? Or it will happen, given enough time. A reaction is spontaneous if the combination of these two terms is negative. All right, so let's look at a specific reaction. This is something we typically do in organic 2. This is a Diels-Alder reaction. And look, we have two moles of reactants that go to 1 mole of product, right? So it looks like the entropy is going to go down, right? It's going to be more ordered. So that's going to be less than 0, okay? Now, but yet we find out that it's spontaneous. How is this possible? Well, it's spontaneous because it turns out that the enthalpy overwhelms the change in entropy, okay? So we know that T delta S will be negative because temperature is always negative, right? I mean, temperature is always positive, right? So T delta S is going to be negative because entropy is going down. 2 molecules goes to 1. But it must be that this has a big enough negative value that the delta G can be negative overall. And since delta G is negative overall, we say that the reaction is spontaneous. Okay? So that's a good example of how these two terms work together to tell us if a reaction is likely to happen. Now let's look at the notation that we're going to use for free energy. It's going to be very similar to the one we used for enthalpy, right? Remember we did enthalpy a little bit ago in a previous one. That was delta H. Well, here we're going to do free energy, okay? And if the free energy of a system goes from high to low, then we would say that we get, that's gone means energy, we get energy out of it, okay? That would be exergonic. It looks a lot like an exothermic reaction, right? But exergonic would be if the delta H is negative, if the free energy goes down. And you would imagine that if the free energy goes up, it's going to look like this, right? You see you've got your reactants here, reactants, products. If the energy goes up, then the delta G is going to be positive, and we're going to call that endergonic, okay? So hold on to your hats. We're going to be using Gibbs free energy, enthalpy, and entropy, and tables from those, right, to our great advantage when we're trying to predict which direction reactions are going to go and how fast they're going to go.